Hi, I'm Victoria Brooks and I'm a veterinary epidemiologist. I'm going to talk through how to calculate the positive predictive value of a diagnostic test result. So imagine you have your diagnostic test. This is one that looks a little bit like a snap test and it's come back positive. But your test isn't perfect, so the sensitivity and the specificity are not 100%. So for example, maybe the sensitivity is 75%. So it's possible that you might have some false negatives. And your specificity might be 95%, for example, and that means that there is a possibility of some false positives. So we did get a positive result on this test, so we're wondering what's the probability that this test result is showing that the animal is diseased, so it's disease positive, given that we have this positive test result. So we can do this using an algorithm approach, sometimes called decision tree approach, or a flowchart. But we do need one other piece of information before we do that, and that is the prevalence of the disease that we're testing for in the population, or sometimes we might call that the probability of the disease in an individual animal. And this can be quite a subjective measurement, so we need to use all the information that's available. So perhaps we might have previous results for this population, or we might have an idea of what probability we might expect in a particular animal given the types of clinical signs that it's showing. So we, even though it's subjective, we make an educated guess about our pre-test probability. So let's make it in this situation. Let's say that we're 60% certain, given what we know so far, 60% probability or 60% prevalence of disease in this particular situation. Right, so let's draw out some of our algorithms. So sometimes animals are disease positive, and if they are disease positive and they test positive, then that's a true positive on the test, and that's the sensitivity of the test. Sometimes animals that are disease positive test negative. They shouldn't have done, but they do, and that is, in which case that's a false negative. And because this is a probability tree, both of these arms have to add up to 1. So if that's sensitivity on that arm, this arm has to be 1 minus sensitivity. And we already have the numbers for this here. So we've got the sensitivity of this particular test. So we can put 0.75 there. So it's put these in the range of 0 to 1. So instead of 0 to 100, convert it to 0 to 1. And this arm here must be 0.25 because that's 1 minus 0.75. Sometimes animals are disease negative, and in this case for this particular test, we can say that if it tests negative, so it's a true negative, then that would be the specificity of our test, which is here 0.95. And in the cases where the test gets the answer wrong and says that it's a positive, that's false positive, and we know that's 1 minus specificity following the same rules as above, and therefore this would be 1 minus 0.95, which is 0.05. So far for our tree, we've filled in the test characteristics. So let's put that down there. Test characteristics. Now, what about the animal characteristics? So we have our animal over here, and even given our test result, we know that the animal either does have the disease or it doesn't have the disease. So the probability of the animal having the disease is our pre-test probability, or probability in the individual animal, or the prevalence of the disease, which in this case we've made it 60%. So let's write that here. So we've got prevalence, and we know it's 0.6. And same rules as before, both these arms have to add up to 1. So this is 1 minus prevalence, which is 1 minus 0.6. So this arm adds up to, this arm is 0.4. Right, so we got a positive test result though. And so we're particularly interested in whether this is truly a diseased animal. And from our decision tree, we can actually already see that there are 2 ways in which we can get a positive test result. We can have a positive test result here or a positive test result here. So true positives and false positives. So let's now calculate our positive predictive value. So positive predictive value equals the numerator here is the true positives divided by the denominator, which is all ways of being positive on that test. So that's true positives plus false positives. And we can now use the numbers on our arms to calculate that out. So the arms that we're interested in are this one here and this one here, because these are the two routes that could have happened. And because we've got a positive test result, there's only two possibilities of the way this could have happened. So this is an either or again. So let's look at this arm first. And we know that the numbers there are 0.6 times 0.75. And then underneath that, for our both arms together, so this is our total possibility, so 0.6 times 0.75, so that's the true positive, that's that one there, plus how their animal can be a false positive, so we've got 0.4 times 0.05, so that's our false positives there. So that's our numerator and that's our denominator. So now let's calculate that out. So we'll get a calculator to do that. So 0.6 times 0.75 equals 0.45 on the top row there. And again, 0.45 underneath here, because this is the same as that. So 0.5 plus, let's do 0.4 times 0.05 equals 0.02. So let's calculate those all together. So 0.5 divided by 0.47 equals 0.96, and we can say that that is 96%. So putting that all together, we can say that given this positive test result here and the characteristics of our test here and the pretest probability here of 60%, our positive predictive value, so the probability that this animal is disease positive, given that we've got this test result here, is 96%. So that is our positive predictive value.